Now Einstein could complete his story. He had come to accept that light always traveled the same speed as observed by any observer. No ether, just an always observed 186,000 miles per second. From that, as he pointed out a few years later, you could already see that time, classical, absolute Newtonian time, was shaken. A clock is really just a phenomenon that repeats over and over again, some motion, some system that comes back to its previous state over and over. Galileo used his own heart as a clock in some of his experiments. A few years after the relativity paper, Einstein had an extremely simple idea that illustrated one of the central features of relativity. He understood that he could use two mirrors, one facing up and one facing down, and that a beam of light, as it went each time from the top to the bottom to the top, could click and function as a clock. That, coupled with the idea that light always travels at 186,000 miles per second, allowed Einstein to illustrate one of the most extraordinary features of relativity, that time traveled slower for a moving observer than for one at rest. To see why it's important that Einstein had a light clock and not a basketball clock, let's do the experiment first with the basketball and see what happens. Then we'll try it with light and see that time really does change. In our Galilean basketball clock, the resting twins' basketball and the moving twins' basketball strike ground at the same moment. The height of each bounce is the same. However, because the moving twins' basketball is also traveling horizontally, left to right, it has farther to go before it hits the ground, and therefore must be traveling at a higher velocity to stay in sync with the still basketball. Now, with Einsteinian cleverness, we change this basketball into a photon. As long as we're still, it makes no difference. Just as in the basketball case, the relativistic twins' photon travels on a sawtooth pattern. The slant trajectory is longer than the vertical trajectory. But the Einstein light clock is different because light always travels at 186,000 miles per second. That means that unlike the basketball clock, where the moving ball has a higher velocity because its slant distance is greater, the relativistic at-rest twin sees the slant moving photon as taking longer to go from bottom to top than his own straight up-down photon. It takes longer to go a longer distance. Punchline: the stay-at-home twin says his clock goes bottom to top and partway down again in the time it takes his slant-moving twin's photon to go only from bottom to top. The stay-put twin concludes, as night follows day, that the moving clock is running slow. What this means is that if our relativistic rhino Victoria were suddenly to charge away at a significant fraction of the speed of light, we'd see everything about her running slow, her watch, her heart, everything, compared with her stay-at-home rhino twin, Bessie. And now that he knew how to coordinate clocks, he could describe precisely how time would be measured in different, constantly moving frames of reference. Imagine a train traveling by you as you stood in a station. Well, two events that are simultaneous for the station are not simultaneous for the train, and two events that are simultaneous for the train are not simultaneous for the station. This was radical, disturbing, an upset to the central concept of Newton's physics. One of the great consequences of Einstein's thinking about relativity was that simultaneity was not the same for a rest frame and a moving frame. Two events that are simultaneous in a rest frame are seen to be not simultaneous for a moving observer. Imagine a train station. Lightning strikes at 2 points equidistant for an observer on the station platform, and the flashes arrive in front of her nose at the same moment. Unambiguous, they started equidistantly, they arrived at the same moment, they are simultaneous. Now those two strikes occur as events in space-time. You could say, are the events in the station or on the train? No, that's not the right way of thinking of it. They're just flashes, they're just points in space-time. The way if I took a tiny pencil mark on the street, that's not in one coordinate system or another. You can assign it different coordinates depending on how you organize your coordinate system. Well, so it is in space-time. There are two flashes that occur in space-time, two events. Now, imagine a train roaring through the station, some goodly fraction of the speed of light, really good train. An engine driver and a caboose driver are equidistant from the middle conductor. That's what it means to be a middle conductor. You're between your front and the back of your train. We imagine that those original lightning strikes occur gently in front of the nose of the engineer and in front of the nose of the caboose driver. But do those flashes arrive at the train middleman's nose at the same time? They do not. Why? They do not arrive simultaneously at the middleman's nose because as the flashes are radiating backward from the front engineer's flash, the middleman is racing towards where that flash occurred. So the flash has less far to go and gets to the middleman's nose first. Conversely, the middleman is racing away from the place in space-time where the caboose driver's flash occurred, and so that takes a longer time to get to the middleman. So what does the middleman conclude? He knows he's the same distance from the engineer than he is from the caboose driver, and he gets those signals at different times, first from the engine and second from the caboose. So he concludes as night follows day that the flash must have been issued first from the engineer and second from the caboose driver. Two events that are simultaneous in the station occur at different times in the moving frame of reference, one then the other. Crucial in our reasoning is that we're dealing with light. Even though the middleman is racing toward the light flash from the driver and away from the caboose flash, the middleman always sees the flashes, both flashes, as traveling at 186,000 miles per second. That's the law. That's what Einstein built into one of his two founding principles of relativity. In the train, two events are simultaneous. In the station, they're not simultaneous for the train. Light always travels the same speed, and it's central to our consideration, central to our conclusion that two events simultaneous for the station are not simultaneous for the moving observer.